Hello everyone. In this video tutorial, I am going to walk you through my implementation of a generic Retrieval-Augmented Generation (RAG) framework with a built-in multi-dimensional evaluation engine. The objective of this project is to build a RAG system that is completely modular, meaning it can dynamically run any dataset and work with multiple LLM providers like Groq, Google Gemini, OpenAI, or Ollama without changing a single line of code. Our default project domain is the history of quantum computing. The dataset consists of 8 highly detailed markdown documents covering foundations, hardware platforms, error correction, post-quantum security, sensing, and chemistry simulations. We also have a set of 15 predefined Q&A evaluation pairs. Let's start with installation. The project is packaged with Windows automation scripts. To install all requirements and configure the virtual environment, all you need to do is run. Install .bat, point cursor to the command or double-click it. Let it show that everything is already satisfied/installed. This creates a Python virtual environment, installs our pinned requirements like ChromeDB, sentence transformers, and LLM SDKs, and runs a quick import diagnostic. Next, we configure our API credentials in a .env file. The framework defaults to Groq using the Llama 3.3 model due to its speed and generous developer tier, but you can also configure keys for Gemini and OpenAI. Let's launch the interactive RAG interface by running run.bat. Because no collection exists in our Chroma database yet, the system automatically reads our 8 documents, breaks them into 500-character chunks with a 100-character overlap, generates 384-dimensional dense vectors using a local BGE small NV 1.5 model, and indexes them. Let's ask a factual question to test the system. What did Google's Sycamore processor achieve in October 2019? Type this question in and press enter. Let the response print on screen. As you can see, the system retrieves the correct document chunks, generates the response with precise specifications, cites the source file 02.quantum_hardware_platforms.md, and shows us a confidence score and response latency. Now, let's ask a harder comparison question requiring synthesis across documents. Compare how trapped ion and superconducting platforms handle qubit connectivity. Type it in and press enter. Let the response print. The retriever successfully grabs chunks from different hardware sections. The LLM highlights that trapped ions offer all-to-all connectivity, while superconducting systems are limited to nearest neighbor layouts. Now let's look at the core of the assignment, the evaluation framework. I will run the evaluation pipeline using evaluate.bat. This script runs all 15 questions from our Q&A dataset through the RAG pipeline and calculates 2 types of metrics. First, quantitative metrics, keyword F1, measuring direct token overlap. ROUGEL, capturing sentence structure overlap. Semantic similarity, using cosine similarity of the BGE embeddings to assess semantic alignment. Fact coverage, verifying if the key facts we defined are present verbatim or semantically in the answer. Groundedness, tracking hallucination rates by checking if generated sentences are mathematically supported by the retrieved context. Second, retrieval metrics. We evaluate the relevance of the retrieved chunks by calculating precision at K, recall at K, and MRR, mean reciprocal rank. Wait for the progress bar to finish and show the ASCII tables on screen. At the end of the run, the console prints a complete summary table of our per question metrics, followed by aggregate averages. It also outputs the results into 3 formats inside the results/folder: JSON, CSV, and a beautifully formatted markdown report. During the development of this framework, we encountered a few key challenges and design trade-offs. Embedding model selection. We chose a local BGE small model because it runs entirely offline, eliminating API network latency and costs while providing highly accurate semantic search. Hallucination prevention. To prevent the model from fabricating details, we set the LLM temperature to a strict 0.1 and engineered strict prompts, forcing the model to rely solely on the retrieved chunks. Unicode portability. We resolved Windows console encoding limits by making sure all print layouts fall back to ASCII-safe formats. This concludes the tutorial. The codebase is clean, packaged using a PyProject.toml file and ready to be deployed. Thanks for watching.